Hello and welcome to another video in this series as we journey from the simple primes to the foothills of the Riemann hypothesis. Today's video is a bit of an appendix because we're going to be talking a little bit more about Dirichlet series. Now previously we talked about the regions of convergence and divergence for the Riemann Zeta function, which is expressed as a series which we're now familiar with. And that series is not a power series in the traditional kind of sense that we're used to. It's a Dirichlet series, and we have a slightly different approach for working out the regions of convergence and divergence. And that's what we're going to look into today and explain how that works. Now, there's a little bit of algebra in today's video, so if you want to skip all that and you're not interested in how the results are derived, that's fine. What we'll do is we'll start off with just explaining the results, so you understand, what Dirichlet series are about and how convergence works. And you can kind of stop watching there. But if you're interested in the full derivations, then this video will do that. As I say, it's a bit of an appendix video, so there'll be a little bit of algebra, a little bit of derivation. So let's dive in. So the Dirichlet series have a general form, which is a sum of terms that look like this. Something like a to the n over n to the s, and it's the n that we're summing over raised to the power s, and s can be complex now that we've seen. This is different from the normal traditional power series, which are a series of terms where the n is an increasing power. This is almost flipped the other way. Now the Riemann Zeta function in the series form that we've seen is an example of a Dirichlet series. In this case, a to the n is just 1. It's always 1, so it's 1, 1, 1. But you can see the n are increasing 1, 2, 3, 4 raised to the power s. And in the last video you saw that for the first time we jumped from s being an integer or a real number to s being complex. So Dirichlet series are the general series of this form, and the Riemann Zeta series, which we're very interested in because it's linked to the primes, is one example, a simple example, probably the simplest example of a Dirichlet series. And what we did in the last video is we tried to work out the regions where this function, when it's defined in this way, with this series, where it converges and where it diverges. And we found that it was relatively easy to show that it converges for sigma more than 1, real part of s more than 1, and also for sigma less than or equal to 0. But we found that it was a bit more involved for the region between 0 and 1. That needed a little bit of extra work, and in that video we skipped over that. And that's what we're going to look at today. If you're not interested in derivation, let me sort of draw a picture just to kind of show you the results up front. So if we have the complex plane with the real part, which we know is sigma, and the imaginary part, which we call it. With normal power series, you have regions of convergence, which are disks. So you might have something like that, and everything inside the disk converges and everything outside diverges. With Dirichlet series, that's different. With Dirichlet series, what we have is not disks of convergence, but half planes. So you might have an entire half plane where there is convergence, and then everywhere else we have divergence. So you have two regions. Let me use a different colour to show that. I'll use red for divergence here. So you can see there is a line at some special sigma, let's call it C, sigma C for convergence, where to the right of it a Dirichlet series converges, and then to the left of it diverges. So that's the main kind of point to take away if you didn't want to watch the whole video. And it's useful for us to be able to work out where that line is, because that tells us where that Dirichlet series converges and where it diverges. We need to find this special sigma C, this sigma of convergence. It's called the abscissa of convergence. Abscissa is just a word that is not very used that often, but you might have come across it in kind of some school textbooks. Now, a common way of working out where a Dirichlet series converges and doesn't converge, where this special sigma C is to be able to say, well, if there's a special, let's say, let's call it x for the moment. If there's a special x where if to the right of it the function converges, but at x itself it diverges, that means we know that sigma of convergence is at x. So the first thing we're going to look at is this idea of, just remind ourselves, this idea of absolute convergence and normal convergence, sometimes called conditional convergence. So a series converges absolutely if we replace all its terms by its magnitude. It's just an example here. So let's start with this series. 1 minus a half plus a third minus a quarter plus a fifth. So you can see it's plus minus plus minus plus minus. And that actually converges to log of 2. We don't have to show that why that's the case here, but that's a separate thing if you're interested. Now if you replaced all the terms by their magnitudes, so that these negatives go away and become positive, and that's the harmonic series. So what we've said here is that a series might converge, but it might not converge absolutely. It's well known that if a series converges absolutely, then it also converges normally. But the other way around, it's not always true. Just because a series converges doesn't mean it has to necessarily converge absolutely. It's useful when it does, but it doesn't always happen. So this simple example illustrates that. So let's focus on absolute convergence first, because that's the easier case. So just diving into a little bit of algebra. I promise that none of the algebra is advanced, it's just simple algebra, but there's a little bit of it. So let's take a deep breath and go. We'll break the discussion into pieces so you can take a break. So let's assume that a Dirichlet series converges absolutely at a point S1. Let's draw a picture. So let's have a point S1, and let's say a Dirichlet series converges there. That's the first thing we're saying. Actually, we're saying it converges absolutely. Now if we have another point S2 where the real part is bigger than the real part of the other one, that means it's to the right of it somewhere. Let's say here S2. So the question is, does it converge or diverge there? Well, we've given you the answer already. We've said to the right of a half plane of convergence it all converges, but let's say we didn't know that. So our ground facts are that it converges at this point. What happens to another point that's to the right of it, where sigma 2 is more than sigma 1? So let's explore that. So let's look at the magnitudes of the terms because we're talking about absolute convergence, the magnitude of an over n to the s1. Now that's complex s1, and we know the magnitude of n to the s is n to the sigma, the real part. We've seen it several times now where it's just the real part, not the imaginary part, that informs the magnitude. Here's a reminder: n sigma plus it is n sigma e to the it ln n. And we know that this thing, e to the anything, e to the I anything, has a magnitude of 1. It's a unit circle. It's a vector. It's a complex number that lies on a unit circle. So the magnitude of n to the complex number is n to the real part of that complex number. That'll become second nature, this, because we will see it several times. So that's why that can be simplified there. Now we know that sigma 1 is less than sigma 2 because sigma 2 is to the right of the other point. Do you remember? Sigma 2 and sigma 1. So sigma 2 is larger. So that means something over n to the sigma 2, where sigma 2 is larger and n is an integer. That means that fraction is smaller. So this is more than that quantity. And then we can undo this packing that we did, this conversion from complex to real. We can say real to complex. That's the magnitude of an over ns2. So what we've just said is that the magnitude of the series, Dirichlet series, at S1 is larger than or equal to the magnitude of the Dirichlet series at S2. Let's do that in pictorial form. The magnitude of the Dirichlet series here is more than or equal to the magnitude here. Intuitively, let's say that in simple words, what we're saying is that for any Dirichlet series, the magnitude of the when we do the absolute terms, the magnitude is larger to the left and smaller to the right. So I can kind of just draw a helpful picture here like that, and we can say at some point it diverges. This is the magnitude. That's just a kind of picture to help. It's not very scientifically accurate. So that we've seen that already with the when we visualized the Riemann Zeta function. We saw that as we went to the right, its magnitude got smaller and happened to converge to 1. But the Dirichlet series all will have a magnitude that's larger to the left and smaller to the right. So that's a nice thing to get a feel for. So we've just said that if the series converges at S1, then it must also converge at S2 because the magnitude is less there. Now, next bit is a little bit about logic really, and it's kind of obvious, but sometimes you have to say it, explicitly. So there will be 3 kinds of Dirichlet series: those that converge everywhere, those that diverge everywhere, and the third option is the ones that have a region of convergence and a region of divergence. In those cases, we can say that the abscissa of absolute convergence is minus infinity, plus infinity, or a finite value. That's not saying anything special, that's just a fact. So let's look again at the Riemann Zeta function. We've already drawn a picture about this. So we know that the Riemann Zeta function, when it's over real values, sigma say, converges for sigma more than 1. We've seen that before. We also know it diverges at sigma equals 1, which is the harmonic series. That means the abscissa of convergence is at 1. So the series converges for all the s where sigma is more than 1. Let's say that in picture form. If this is 1, what we're saying is that at any s where sigma is more than 1, it converges. We know it diverges here, and to the left of it we know it diverges. So we've talked about the absolute convergence, where each term is replaced by its magnitude, and in some ways that's an easier case to deal with. Let's remind ourselves why absolute convergence is different from conditional convergence. If some of the terms have negatives that we saw, so we saw earlier on up here, they can take away from the partial sum. So 1 minus a half reduces the sum plus a third, but then take away a quarter, reduce. It stops the partial sums growing so fast. So in the harmonic series, they grow so fast that it diverges to infinity, but the negatives here counteract that growth. When it comes to complex numbers, the same thing can happen, and this is a very simplistic example where we say e to the I pi, that's minus 1, can cancel partly the effect of another term which might be 2e to the I 2 pi. So you can see in this simpler example with complex numbers that this term limits the growth of this term, so 2 minus 1. In fact, more generally, if you have complex numbers which are obviously have a direction, you can see that you might have something like this, where there is a convergence happening, but it's only possible because we are taking into account the direction, the angle of those complex numbers, not just the magnitudes, because if we do the magnitudes, they would keep growing, whereas here if we take into account the angle, because we're taking into account the imaginary part, then you can find that the sum kind of loops back on itself, the partial sums. So that's the reason, that's the insight into why absolute convergence is, I guess, a stronger condition than normal convergence. So what's our strategy then? What we're going to do before we dive into the algebra, it's useful to see what the overall plan is. We're going to show that if a series, and this time remember we're not talking about each term replaced by its magnitude, we're dealing with a more difficult case where there are either negatives or other complex numbers. We're going to say that if that series is bounded at an S, we're going to show that it's bounded to the right of that S. And then we're going to push a little further to show that actually at this S to the right of S0, it actually converges. That's our overall strategy, and it starts with the condition that it's bounded at S0. Let's draw that as a picture. So if we've got S0 there, and we're saying that it's bounded, what we're going to try and show is that to the right of it, at an S to the right of S0, it is also bounded, but then we're going to push a little further and show that it converges. That's the overall plan. And it's useful to see that overall plan before we dive into the algebra. So we'll start with a Dirichlet series, and we said that it's bounded at S0, that's our starting condition. And we're going to look at the partial sums. That means we're not adding up all the way to infinity, we're adding up all the way up to, say, x. And we're saying that it's always going to be less than a bound m, the magnitude. That's what we mean by bounded. So no matter how big x is, it will always be less than m, the magnitude of the partial series, even if we did go to infinity. So just a reminder, being bounded is not as strong as being convergent. If you are convergent, you are bounded, obviously, but bounded means that your partial sums can oscillate, like we saw with that spiral, but they will always be less than some limit, call it m here. Now we're going to use something called Abel's partial summation formula. Now that, again, we'll have a separate video explaining where that comes from, but it's a very useful tool because this formula helps us convert a problem from being a sum into an integral. And when things are integrals, they're we can work with them. We've got tools to analyze. We can do calculus, for example, on closed forms, whereas it's a little bit more difficult with discrete sums. So continuous maths is sometimes easier to analyze than discrete maths. So this is saying that if we've got a sum over integer n between two limits here, and we've got terms bn and a function f of n, that's the same as capital B of the upper limit times the function of the upper limit minus capital B of the lower limit times the function of the lower limit. We'll explain what capital B is in a second. Minus the integral of capital B times the first derivative of that function. Now this capital B is always defined as the sum up to x. So B of x is the sum up to x, up to and including x, of those coefficients Bn. Now when you're using this partial summation formula, the trick is to work out what the best choice of Bn and Fn are. So what we're going to do here is choose Fn as, or Fx as x to the s0 minus s, and that makes sense because we're thinking about 2 points, s and s0, and then Bn, if we choose it as an, and remember an is the coefficients from our Dirichlet series over n s0, when we multiply these things together, Bn times Fn, we get our original Dirichlet series. So that's the good combination to use. So what we're saying is our Dirichlet series between two limits is Bn times Fn with this choice. Now Bx, it's the sum of these terms, because that's our choice for Bn, an over n s0, and we can say because that's s0, this is bounded. That was what we started with. We said the sum of an over n s0, which is the Dirichlet series at s0, that was bounded. Its magnitude was bounded. So what we've said is our original Dirichlet series can be expressed using this choice of Bn and Fn, and then using this partial summation formula we have B of x2 and F, remember, is x s0 minus s. It's that thing. So this is a lot of algebra, and if you want to follow it, I would recommend you write it out yourself with pen and paper. It's not difficult at all, the steps. It's just there are some steps. The same with this term. Nothing difficult there. And then the thing to do here is, remember, this is the first derivative of f, and we can take that and it becomes, if it's a function of t, then we can easily work out the first derivative, and it becomes t to the s minus s0 plus 1. So we have a chance now to actually perform this integral. But before we do that, we're going to use a triangle inequality. We're going to say that the magnitude of this thing on the left is less than or equal to the magnitude of all of these terms if they're added together. Why is that? We use triangle inequalities a lot in number theory. So if you've got something like A equals B minus C, then we can say the magnitude of A is less than or equal to the magnitude of this thing, B, plus the magnitude of this thing, C. That's always going to be the case. And if there was a D here, plus D, not minus, we'd say the same there. So what we're saying is we're adding up the magnitudes of all these terms, ignoring their signs. If they were negative intrinsically, we just turn them positive because we've got magnitudes here. Then the quantity on the left will be less than or equal to the magnitudes of the individual quantities So the magnitude of the sum is less than or equal to the magnitude of the parts. That's the way to remember it. So yes, there's a minus there, but we're taking 1, 2, 3 terms and looking at the magnitudes of all of them, there, there, and there. So although it looks complicated, all we've done is just applied magnitude terms. So the magnitude of the Dirichlet series on the left is less than or equal to the magnitude of the 3 bits. So 3 bits, ignore all the complex, all the kind of complicated looking expressions. And now what we're going to do is, again, simple algebra, but just a fair bit of it. This, remember, was bounded less than or equal to m. This is also the same thing, bounded. It was always less than or equal to m. So we've got m there. And this is complex s and s naught. Remember, the magnitude depends only on the real part, the sigma, so we can do that. Same there. Here we've got s minus s naught, so we can take the magnitude of that. The magnitude of b, t, is always less than or equal to m. Remember the bound? That's there. And then we've got this bit left to evaluate. Now this thing is now real because we've got just the real part of s, which is sigma naught minus sigma, and that's minus 1 there because we've turned the fraction upside down. So if you want to kind of, do this with pen and paper just once to work it all through, it's a good thing to do, and once you've done it once you probably never have to do it again, but it's just a useful thing to do once to see and get a feel for where this thing has come from. And again, more bits of algebra. We've got 2 quantities here, so sigma is more than sigma naught, and therefore this quantity is negative, the power. That's why it's less than 2mx1, sigma naught minus sigma. We've got m x1, sigma naught minus sigma, mx2 plus m x1, sigma naught minus sigma. Now the first thing to say is that sigma naught minus sigma is less than 0 because sigma is more than sigma naught. Just remember sigma and sigma naught. So if we're raising something to a negative power, the smaller it is, or the larger it is, then the smaller it is if we raise it to a negative power. That means this is less than, so m's just a constant in both cases, x1, if we have 2 of those, sigma naught minus sigma. That's where that comes from. Because this quantity is smaller than this quantity. So let's say 1 over 4 is less than 1 over 2. And that's why 1 over 4 plus 1 over 2 is less than 1 over 2 plus 1 over 2. That's effectively what we're doing here. I hope that's clear. If it isn't, do comment and we'll talk about it more. We know that sigma naught minus naught, we know that's less than 0, but x1 is smaller than x2. If we take the magnitude there, this term is larger because x1 is smaller, so we can put that up front, and that's less than, if that term is larger than that one, that means together they are less than the first term, which is less than twice the first term. That's a bit of arbitrary algebra. You might think, why are we doing that? Why are we trying to get to 2 times something involving x1? It might be true, but how is it helpful? Well, it helps with this. If you replace the term here with this top term, this top thing there, with this, then we can say the Dirichlet series, the magnitude, is less than to mx1, and then we can simplify into this expression. Try it yourself. It's, you know, I'm not going to lie, it's actually a little bit boring, the algebra, but if you want to know where it's come from, this is where it's come from. There's nothing particularly insightful about this algebra, but it's worth just going from A to Z just once. This, at S0, this is bounded, this Dirichlet series. At a general S, to the right of S0, the magnitude is less than this quantity, and that quantity consists of terms which are also bounded, because sigma naught minus sigma, that's fixed. S minus S naught magnitude is fixed. x1, the starting point of that series, is fixed. M is fixed. So this whole thing is a bound. So the key point is that if the series is bounded at S0, then it's also bounded to the right of S0. So we did the hard work to arrive at that, but that's an important fact. So let's say that in pictures. So if a Dirichlet series is bounded at S0, then it is also bounded at an S to the right of that S0. That's what we've shown. Now we want to see if we can push that to convergence, because that's what we're interested in. So let's do a little bit more algebra. That's written up the results we found so far, and what we see here is that this chunky expression can be written as something k times x1 raised to the sigma naught minus sigma. When we look at it this way, we see that the k doesn't depend on x1. We've just got this bit, x1 raised to the power of sigma naught minus sigma, which is less than 0, remember. Only that depends on x1. There's no x2 in this, remember now. If we let x1 go to infinity, this thing tends to 0. What does that mean? That means the tail of this series goes to 0, the magnitude of it. If you have a series and the magnitude of the terms gets smaller and smaller, then it converges. That's either very obvious or you have to think about it a little bit, but it makes sense, because if it didn't go to 0, then the sum, the sum would keep growing. Let's illustrate that in picture form. So if we had partial sums, let's say sum up to n, so that's n. And that's the magnitude of the sum. The sum grows, and that means if we take the tail, the magnitude of the tail, the terms get smaller and smaller, because when we're adding less and less to the partial sum. So what does that mean? That means that actually this converges. It's not just bounded. The fact that the tail goes to 0 means that this series, the magnitude, is bounded, is actually convergence. So that's quite a powerful statement. So let's draw that on our picture. We've said if a series is bounded at S0, then it is also bounded at S to the right of S0, but actually it also converges at that S0, at that S to the right of S0. This ties in with our big picture, where we know that we've got this picture in our head from the Riemann Zeta function, but it wasn't immediately clear that boundedness to the right of a point means convergence. You might think, well, does that mean the point S0 also is convergent? Not necessarily. It could be, but not necessarily. But if we do find a point where the Dirichlet series is bounded, then anywhere to the right of it, it converges. Great. Phew, that was a lot of work. So let's take a breather and summarize the results. So, we've said, if a Dirichlet series up to x, so it's not up to infinity, actually it could be, x could go up to infinity, if it's bounded at S0, then the Dirichlet series converges for any point to the right of it. That's the main takeaway. So we can think about a special case where S0 is 0. So if S0 is 0 there, then n to the S0, n to the 0 is 1. We're looking at a series of just the coefficients. Now if we can say that that series of coefficients is bounded, then the Dirichlet series converges for sigma more than 0. That's a useful special case that we find ourselves using quite often, and we can look at an example of that later. So sometimes just by inspection, by looking at just those coefficients, those an terms, if we can see straight away that they're bounded, not even convergent, just bounded, because they might oscillate, we can then say that the Dirichlet series converges for sigma more than 0. That's quite a powerful thing just to be able to say just by looking at a series. So similar logic to the abscissa of absolute convergence, we then have again an abscissa of convergence, not absolute convergence, just more general convergence, where to the right of a sigma of convergence it converges, and to the left it converges. And importantly, on the line itself, we can't say necessarily that it converges or diverges. That's something we have to work out separately. So let's apply this, particularly that special case that we talked about. So we'll find that this alternating zeta function is useful. We'll see why soon. It'll turn up in our journey. Similar to the Riemann Zeta function, but actually the terms are alternating, so there's a minus, plus, minus, plus. So it's like the Riemann Zeta function, but the terms are alternating, and this is how we can write it: -1 to the power of n plus 1. Now, you might say, well, we know we've done a lot of work around convergence of the Riemann Zeta function. What about this function, this eta function? Well, if we look at the we saw before that if we can look at just the terms by inspection, the coefficients, 1, -1, +1, -1, +1, -1, +1, there it is. That oscillates, but it's always bounded less than or equal to 1. It never grows more than that at S0 equals 0. And our conclusion from that was that therefore this series converges for sigma more than 0, and that's a useful result that's easily found. So that pops out of this Dirichlet theory, and we'll use that later. So we'll stop there. That was a bit of a slog in terms of algebra. We've got a few more of these appendix type videos coming up, which you can choose to kind of dig into. But as I say, the main conclusions for this were kind of drawn in picture form at the start. And the main point there was that Dirichlet series converge in half planes, and often we only need to find the rightmost point at which it kind of diverges, and that gives us the kind of the region. So I hope that was useful, and it helps us explain some of our results when we looked at the Riemann Zeta function as we took it for the first time into the complex plane. Great, see you next time. Bye.